All right, it's staying on now, but it's going to screw up again.
Somebody took it.
All right, it's working for now, but it's going to stop working in about 30 seconds. So apologies when that happens. So thanks everybody for coming today. My name is Jack Mannino. So we're going to talk today about containers. So containers are kind of changing the way we've been shipping, building, and deploying software for a few years now. Once upon a time, we built things monolithically. So we built these really big stacks of applications, and we didn't really use that computing power too well all year round. The cloud came along, and suddenly we wanted to scale things horizontally. So containers are a really perfect way to do that. And containers do a lot in terms of reducing the attack surface, but nothing's perfect, and there's quite a few ways we can still kind of hang ourselves in a lot of different ways. So today we'll look at what the container runtimes themselves provide in terms of different isolation models. We'll look at some things that are available both in the Linux kernel as well as in modern container orchestration systems. And we'll just kind of have a goal of that we wanted to make it hard for the container to essentially, if it's popped, we want to make it hard for that to let you move laterally throughout a cluster, maybe even elevate privileges. And we also want to make it hard for other containers to compromise other containers as well, right? So we can do a lot at the application layer to harden things, but we can screw things up a couple layers above where the container runtime actually happens at the orchestration layer, and everything breaks down there as well. So that's me. My name is Jack. I don't live in a van down by the river, and that's me teaching my daughter manners on the right-hand side. Mostly I write in Scala and Go these days. I did some time as a pen tester. I still enjoy breaking things. But I tend to focus a lot more on defense, and I write a lot of code these days. And I run a company called Invisium, based in the East Coast. We focus on software security and helping people build secure software. So once upon a time, we had virtual machines. So VMs came about, there was earlier work in the 70s and 60s, but really when we started using them, was like the late 90s. So VMware came around, and they made x86 virtualization easy enough to use. And so we worked with hypervisors, and this worked pretty well, right? And we still use VMs, obviously, in a lot of places where VMs break down is that we have to allocate a lot of resources for services that may not need them, right? So containers allow us to scale based on the way we actually compute these days. FreeBSD jails came about, worked a little bit differently than a hypervisor, doesn't try to isolate things quite as deeply. But gives everything its own perspective, the file system, processes, users, and so forth. So that's not quite as deep as a hypervisor, but some separation. And then we went to SELinux in about 2005, and they introduced containers and zones. So containers and zones allow you to pretty much have some shared kernel. Newer versions, later, I believe it was earlier part of the decade, where they introduced the ability to have separate kernels where your containers run. There's a lot of things that were borrowed from the way SELinux implemented containers that kind of happened in Docker. 2013 onwards, that's where everybody kind of got on the container bandwagon. So it's like, yay, Docker. Everybody wants to be Dockerized. And there's a lot of great things about running containers. But where Docker really got it right is that they made it easy for developers to use, and they made containers developer-friendly, right? So once upon a time, containers were harder in the LXC type of days. Docker kind of got it right. So Docker kind of set off the current craze. But what we're seeing now is that you have a lot more container runtimes starting to pop up, and you have more flexibility with the container runtimes you can run due to things like OCI specification, and things like CRI and like container runtime interface, which lets you use different containers and not have to write as much spaghetti code at the orchestration level to do that. So spoilers, containers really aren't a great sandbox by themselves. So think of things like Docker. You're still using a shared kernel for the most part. So what ends up happening is you have isolation through things like control groups, and you have isolation through namespaces, but you're still sharing a fair amount on the host system. And there's a lot of ways where you can also, do things like share process IDs, share underlying IPC, host network. So beyond what Docker provides out of the gate, there's a lot of implementation ways to kind of hurt yourself, and this also applies to other container runtimes as well. What you find is that you end up kind of relying on some type of rule-based execution for security. So we rely on things like seccomp pretty heavily. We rely on things like AppArmor. to get some kind of sandboxing on top of what that model provides. Which obviously, just by a show of hands, who wants to teach like their Java developers about SELinux when they go back to work Monday? Right? Like there's not enough alcohol in the world to do that. But at the same time, like they're Java developers, right? They don't necessarily have to know how the kernel works. And in theory, they stay in like a garbage collector world. They know it's good. But nowadays, we kind of find that these relationships are breaking down, right? So, I see shops where like the full stack developer works on like UI, API services, container configurations. They run like the registries, and like they also run like production Kubernetes and the AWS accounts, right? So you do kind of have this blurring of roles where people have to learn more. But there's some things that are just absurd to think that anyone's actually going to get these right that's not trained in these things. So in reality, we have the container, and the container generally fits into a pretty big system, right? So we're not running a shell script and then looping over basically running and scaling containers. We're generally plugging them into either a managed container service. So think of like things like AWS and their ECS service, or we think of container orchestration systems like Kubernetes and Mesos, where we run these. So here's an example. Here's your container runtime. So that could be one container running across different nodes, right? So things that maybe have to be shared include things like state, things around security and access and so on and so forth, things like network rules, right? These actually have to traverse multiple nodes in some cases. So kind of that, typical mandatory and discretionary access control model also has to map across nodes as well. So when we think about, keeping you in the container runtime, that's one layer of isolation here. But, we can also attack other services, right? So what we often see is that people will deploy containers, with, shared privileges, which means pretty much, one container could essentially run shell commands in another container using, things like Kubernetes API, right? And that's just normal behavior based on an implementation bug. So, sometimes we can have that. We can also go and start attacking the host itself. So if we have network access, we can do things and abuse different APIs that are exposed on these systems that'll get us, privileged access upstream in the cluster. We can also basically go upstream to attack things. So each container, for example, in Kubernetes is mounted with a secret, which is essentially just basically a JWT token that allows it to use it as a bearer token to authenticate to the API. So imagine basically all your containers are running with the same shared credentials, running with the same service count. Well, then they use that same bearer token to do API access, and you can pull things back like secrets. You can affect the state of other containers. You can even do things like running arbitrary shell commands in any container you want, just because of that shared. So it's not actually shared at the container level. This is actually happening at the, for example, qubit level, and how that's actually running the container runtime and how it's sharing those privileges. So in reality, your containers are kind of isolated, but once they start to move inside of a real system, you have a lot more ways to get into those containers. So here's the gateway drug. Here's a Docker file. So it's a container manifest. And what we can do there, for anyone that's never seen a Docker file before, which I imagine most of you have in here. So for starters, we have a base image at the top that we extend. So from here, we're extending Golang base image. From there, we can set users that we want to use. We can set things like environment variables that get passed in. So often you see people do things like pass secrets into the container. And there's better ways to do it because, like I said, you also have a place where you do mount things like secrets. And that includes, secrets that we use to say authenticate to like a database or so on and so forth. So you generally want to pass these in via environment variables because, every process inside of that container is going to be able to read that, right? Which is a no-no. And we could do things, for example, like install packages. So we're running things like apt and yum, depending on which type flavor of Linux and package manager you want to use. But we need privileges to do that, right? So when we're building those containers, to do things like install packages, we need to run with, pretty high privileges. So when you see now some of the rootless kind of container models now, they don't build things the same way, but they'll run with privileges and kind of build a snapshot, and then they'll incrementally build what that container looks like. So, this is kind of how we've done it, which is basically root in very privileged containers. And that eventually gets basically built into a container package that includes full OS, all those packages, and then any code and files you ultimately transfer over to it. And on the right-hand side, that just kind of shows you the stack there. So Docker's changed a bit over time. But essentially Docker has containerd, which runs as a daemon on a box, and then runc is the actual runtime that runs your individual containers. So with regards to isolation models, we have a couple different ways we can approach things. The first is the Docker way, and Rocket, LXC take this approach where we use control groups and namespaces to isolate things. This has also been the source of a lot of different container escapes over time. And I'd imagine over time there'll be more of these, and there's probably other ones that haven't been found yet. These are implementation bugs. It's definitely hard to kind of get this right. There's a lot of things to consider. What you're seeing is user-space kernels is another option, basically where we run the kernel completely in user space. So if anyone's looked at something like gVisor, I think that's one of the coolest projects out there right now. So they've re-implemented a lot of kernel stuff in userland, where basically you're not actually running syscalls directly on the underlying kernel, but you're running it on a userland kernel. There's obviously some syscalls that have to kind of bounce down to the host, but there's at least a layer of isolation that limits the pool of syscalls you can run. That obviously is going to break some things that are dependent on the full stack of syscalls being there. But nonetheless, this is kind of a good model for getting you a little bit more cleanly isolated. And then we have kind of bringing hypervisors and VMs around. So Intel launched clear containers a couple of years ago. This has kind of been reborn within the Kata containers project. But this basically lets you run the container runtime you want. Obviously, there's things like shims and all kinds of complexity behind that. But it ultimately lets you run things inside of actual hypervisor, which gives you another layer of abstraction between the container and the actual host itself, which gives you the isolation you may want in a multi-tenant environment. So with regards to how the different container runtimes stack up out of the gate, Docker, in my opinion, is still probably the clear winner here. So things that modern container runtimes should provide include things like hardened AppArmor policies out of the gate and some kind of hardened seccomp, right? So Docker provides these things where they've actually kind of pulled down out of the gate. If you run, say, using their seccomp policy, you're running a very limited set of syscalls at that point. They've also done a decent job of limiting the capabilities that a container can actually use out of the box. So if you need certain things like cap sysadmin, you actually have to ask for those things, which is a huge win, right? Because how many of your developers know that they're deploying containers with like ptrace and cap sysadmin, and they have any clue what those things do, right? They don't. So again, having these things fixed out of the gate is pretty nice. Where things kind of suck is that people turn them off, right? So how many people have like had SELinux complain about something and they've turned it off, right? I know plenty of people that do that, myself. But the reality is that you do see people, and I've seen this in the real world, where people will just go in, they'll need something that a container needs to do, it'll throw some exceptions, they'll Google really fast, it leads them back to Stack Overflow, and they end up turning off things like seccomp and AppArmor, right? So here's these great inherent things that people have thought of and they've packaged the container technologies with, and here's reality that people just turn this shit off because stuff needs to work. So for starters, you should use base images that, first of all, support things like seccomp and AppArmor and SELinux, right? So you can use images that aren't compiled for these things. You should certainly check, right? Especially if your developers are just pulling in images from Docker Hub, and they have no idea what they're actually extending and they haven't actually run those things. Definitely make sure that these things are actually present in the base images you use. You always want to make sure that you're using specific image tags to deploy things instead of latest, because when you use latest, you lose control over versioning, right? So you can pull in who knows what, right? So to keep control over what's actually being deployed, make sure you're always using some kind of image tags there. You do want to use as small of an image as possible. Usually, right, you want to limit the amount of utilities and ultimately post-exploitation tools that are available. So Alpine's had its own issues in recent times, right? But Alpine is generally a smaller image. Things like that, right? You don't want to use the biggest image possible. OCI is definitely helped standardize a bit of this. So most of the containers now do conform to OCI specification. So for example, these are the default capabilities that you'd require out of the gate in OCI land. In reality, Docker and others do extend that a bit, but you do start from a really minimal set of capabilities, right? So in reality, if you're going to run with these three capabilities, maybe things break. But this is a better place for container technology to extend from, in my opinion. So things like AppArmor, being able to control things like capabilities, any container runtime should ultimately support these things. It's definitely important to be able to drop capabilities. So control groups and namespaces are a pretty common way that container technologies isolate things. One of the challenges is that things aren't always broken up by namespace. So think of things like time. There's actually not proper namespace in between what happens to the container and host, so those things propagate back to the host. So where people are going to probably run into things, especially as people build new container technologies, is relying on these things and kind of getting the implementation wrong. So again, container escapes that have happened have been around not getting these things right in the implementation. Here's an example of how gVisor does that in comparison. So if we're running Docker, ultimately we're passing things like syscalls to the host, but we're using things like seccomp and rule-based execution models to prevent that, right? So that means we need to get things like seccomp right. Whereas something like gVisor, for example, it actually limits that a bit. You do lose some of the control, right? So things like SELinux and AppArmor get a little bit harder. And there's things that work not quite as well, right? So this is kind of a gray area where maybe doing some of these same configurations in Sandboxing gets harder. Kata containers is another interesting one. So it actually uses QEMU Lite as the actual virtual machine around it. But basically what you end up getting there is that your containers are actually running inside of a true hypervisor at that point. So Docker, in reality, has a layer of separation. So if you were to basically pop that, you wouldn't necessarily get that same privilege to the underlying host where you can then attack other containers and do real damage, right? So then you're going to need a way to get out of that as well. So, you know, at the very least, you've made it harder for an attacker, but you haven't made it impossible because maybe somebody's sitting on all the exploits they need to get out of that container, right? But depending on your tolerance for risk, right, choose your own adventure. So user namespaces are a thing that we can use that are actually underused just because it hasn't been as good of upstream support in container orchestration systems. But essentially what ends up happening there is that we end up remapping the users that are using those containers on the host system to highly unprivileged accounts. So in the event that you can actually get out, you're a little bit more limited in terms of what you can actually do on that host system. Docker supports doing user namespaces and remapping of those things, but this is something that I find a lot of people don't use. And this is a good feature that just gives you a little bit more protection in the event that somebody pops your container. So with regards to implementation issues, so in a Kubernetes land, if you're using Mesos, what you end up getting is a service account that runs per container. Or more specifically, per pod, if you're talking like Kubernetes terminology. So what ends up happening is that they have similar privileges. For starters, they get mounted with the same secrets, but they also have similar privileges to the underlying host and, you know, things like network namespaces and so on and so forth. So you can obviously break down all the kind of walls that you get in isolation and, you know, pick your container runtime, because at this point, you can do things like run shell commands, you can do things like, you know, read their mounts. You can do things like stop other containers. So by default, if you create like a new namespace, and everybody knows in Kubernetes, it uses like the default account for each namespace. So if you don't set an explicit service account to run that with, it defaults to that. So you find that when people and, you know, developers just creating new pods and new services, they generally don't create like, you know, new service accounts. You can enforce those things at admissions, but not everyone does. You can run shell commands because basically there's essentially at the kubelet there's the ability to, you know, run shell commands, and there's an exec service, right? There's a couple different things that you can communicate into the containers with. So pretty much if a service account has these privileges for another container, then it can arbitrarily do these things. So there's an example of like making an API call. You can add, you know, additional command and parameters to do things. But that just gives you an example of what you can do, just by simple API calls. So you can use that service count token, as, you know, authentication header as a bearer. And you can make, API calls if you have network access to do that from the container. So this isn't like the hardest problem to solve, and you can break it fairly easily by using a service account per pod. So in this example here, we create service account, and then we actually in the pod specification run with that service account. So in theory at that point, you're running with separate accounts at that point, which they're going to have separate abilities to do things like pull secrets. Obviously you can overprivilege things, and you can overprivilege those service accounts by the groups you drop them into at the cluster level, but out of the gate, if you kind of do this kind of approach, then you break a lot of those attacks. So you can still have, for example, a container that you've overprivileged, put it in, a system group it shouldn't be in, or somebody that has cluster admin, or some highly privileged, you can't stop them from doing this, but you can stop another service from attacking your microservice, right? But this is an example there of where, if you're going to handle this, you probably end up handling this like one layer above the container itself. Don't share anything from the host. So this includes things like mounts and volumes. So you can do things like mount shares from the host, and you can do things like share things between containers, which leads to all kinds of issues, things like race conditions, overriding, collaborating things that you shouldn't be able to, being able to overwrite configurations on the host, anything you can think of. The less of these holes you enable, the better. And this example, I don't know how well you can see that all the way from the back there, but this is an example. Let me see if I can make that bigger for everybody to enjoy. Yes, great. In this example here, if we're running Kubernetes, this is an example of using a pod security policy, and essentially what ends up happening is that any containers being admitted to the cluster are going to have some of these things in place, or you can actually deny them admission. So in this example here, we're at least saying that it doesn't matter what you've done at the container, or at, say, for example, the pod level. When you're being admitted to our cluster, we want to make sure that you can't share the host network, IPC, process IDs. We want to make sure that you can't actually run things as root. So we can set a range of numbers that basically starts 1 through 65535 to deny root for groups and users. This is a pod security policy. So when we actually admit our containers to the cluster now, we can actually enforce some of these things. So if you're using something like OpenShift, then that's security context constraints. And we can actually apply different policies depending on which groups different containers are a part of based on role-based access control. So we can have really, really, really restrictive policies for certain types of services, and then we can relax that a little bit. What I've found is, does anybody use things like Twistlock in here or tools like that? Not going to totally rag on things like Twistlock, but maybe you have to run them with ptrace and capsysadmin. So hypothetically, you see people do things like run those namespaces with things like capsysadmin and ptrace, and then they have less restrictive ones elsewhere. But you could also screw that up really bad, right? So you do see in reality that people have to run these things with varying levels of enforcement depending on what those systems actually need to be able to do. But this is a nice way to pretty much set it and forget it, because everything that's going to be emitted to a cluster is going to have to conform to these things. And things like bind mounts, read-only attributes to things, right? If you do need to basically make some things available, try to make them read-only. And generally, you don't have good egress filtering from containers, so by default, things can talk outbound, but it's harder to get in, so you have to expose ports from the container, and then at something like Kubernetes, you also have to expose a container and its ports as a service, which just basically opens up some magical IP table rules and lets you route into the service in the cluster. So in what I've seen, it's a lot harder to get in sometimes than it is to get back out. So if our, goal is to basically get back out and, either establish C2 or, move laterally within a cluster, then it's pretty much game on if we can compromise, a single container most of the time. And I've heard that one. It's we have a firewall in it, and that's why we all have jobs in this room, right? That's great, but in reality, you're going to have that firewall, and there's going to be something that someone's going to pop and move laterally, right? There's a reason everyone in there has a job. So, that's usually where we end up. We have a lot of systems that people will, inside of a cluster, a containerized environment, people still have a lot of ways to call back out to the internet. That includes, build servers and places where we're building our containers and registries. We still need to do things like pull down packages, A lot of times containers still need to build things from GitHub, Docker Hub, so on and so forth. So inside of these environments, we generally do have something that we can pop that we can get back out to the internet for. I haven't seen really many scenarios where like we haven't had something that you can still get back out with, right? Jenkins is a great place. So this is, again, something you can solve at the orchestration layer. So you can pretty much apply things like network security policies that do, at the very least, everything egress. This is obviously going to break a lot of things, but this is a default deny to start from. And this is something, again, that if your container's running inside of an orchestration environment, then this is just a good place you can control that at the kubelet layer. And this is another kind of thing that borders into kind of religion. So using things like sidecars, so things like Envoy, if anyone's used Envoy or Istio in their environment, basically what we end up doing is we will deploy a sidecar with our container. And that sidecar is responsible for doing a lot of things security. For starters, it handles things like mutual TLS between our services. So we can do, identity-based whitelists with regards to which microservices can talk to other ones. And we can handle all that via, PK infrastructure that's handled magically by things like, Istio. I'm sure, just by show of hands, anybody in here, actually used Istio, deployed it, messed with it, using it in their shop? Istio is super cool. It's a security layer built on top of Envoy. Envoy is a Lyft project. It's like an L2, L3 proxy. Super cool. And allows you to do things like distributed tracing. So if you want to have visibility with which microservices your containers are talking to, it gives you the ability to do that in a distributed environment. And it also gives you the ability to abstract your container from a lot of those security rituals like mutual TLS, outbound connections. So the Envoy, for example, can also do some of the filtering for egress traffic. And you can push those configurations down magically in a central way with tools like Envoy. So this is one of those places where it gets kind of religion-y these days. Do we want to build really rigid network policies and use things like Calico and Weave, or do we just basically want to drop in something like an Istio and use like a service mesh to handle these things? Pick your poison, right? But this is a design pattern that we can use to kind of absolve ourselves from actually thinking. Capabilities are an important one. So once upon a time, root was super powerful, and we've broken down a lot of what root can do into a set of capabilities. And inside of containers, we can actually drop capabilities fairly low depending on what the container needs to do. So Docker by default runs with a reasonably restricted set of capabilities. You can add capabilities, you can deny capabilities, you can drop all, you can add all. This is one of those places that I find most people overprivilege their containers. Even using the Docker defaults, there's usually a couple things you can also skim out of that as well. But nevertheless, you have the ability to reduce the capabilities that your container can run with. So if you need to, for example, just do things like ping, you don't, for example, need things like DAC override, right? So that's what root uses to do to walk through walls of file permissions and things like that. So there's a lot of things that you can trim out of the container if you don't necessarily need to do those things at runtime. Things like rootless containers are actually becoming a reality where we can run containers that don't actually need to assume things like root privileges to do things like install packages. So like I said, they use a snapshotting methodology to do that. The biggest challenge to doing things like rootless containers has been running those upstream in container orchestration services. So you're kind of seeing a pattern that the containers, they'll implement these things, and then we have to figure out a way to kind of make those security settings run at scale. Because sometimes we're breaking down how the Linux kernel is supposed to be run in a distributed environment. So as of Kubernetes 1.12 that actually just got released fairly recently, you actually have the ability to run things like rootless containers. So if you're doing security context, you actually can set the pros mount attribute, and you can specify ultimately different things that can be masked. You can leave off masks. So if you were to look at, for example, all of the issues open about doing these things, everything breaks, from the things you can mount to the capabilities you have. So things like Docker weren't built for rootless, but they've ultimately shimmed that functionality in to containers nowadays. So, What? Yeah. So, like you said, it breaks things like Istio. So here's like utopian security. Here's what's actually usable by the technologies we want to use, right? So you do find that a lot of cloud-native container orchestration types of shops, everybody kind of likes to pull in the coolest toy. Istio, for example, a lot of shops are using it for a bit, and there are a lot of implementation bugs. So you do find that people do pull things. You find things in Kubernetes have been labeled experimental for about 3 or 4 versions. So kind of, choose your own adventure. No new privileges. So this is something that was introduced a while ago in Linux. So using things like no new privileges, we can limit what containers can ultimately do, or a process can do, to elevate privileges. So for example, if you were to use set UIDs, things like that, you would actually have like your affected UID could be your current user as opposed to having anything elevated. And it makes it harder, obviously, if you don't have root, or, for example, if you limit some of those syscalls to be able to do things like set UID and stuff like that, you make it even harder. So by using Docker, you can set the no new privileges flag, and that'll prevent elevating privileges by setting those flags on different binaries. And in Kubernetes, you can do it within a pod's security context constraint. So the difference there is that if you do that in Docker, that's basically like a command line flag. If you do it in Kubernetes with that constraint, what ends up happening when it runs it in the kubelet is it ultimately just runs it with that flag. So it's a really pretty wrapper around, pretty much like a runtime flag. Read-only containers is another thing we can do, where we can run containers with a read-only file system, root file system. In a lot of cases, this breaks things, right? So this is not a feasible thing for every type of application we want to run. And, sometimes we want to run stateful containers, right? So we talk a lot about doing things statelessly, but not everything works well in a stateful way in a container, right? Things like distributed databases and Cassandra's of the world, right? Those don't necessarily work quite as well there because we still need the distributed state. So some of these things may work well for your type of container and some don't, but if you have a model where you can run read-only root file systems, then this is ultimately another place that we can limit what you can write to, overwrite to, elevate privileges, and ultimately jump out of the container. Container entitlement. So this is a new kind of way of looking at what containers can do. So we've talked about kind of a hodgepodge of, if we lock down this setcomp syscall, this syscall with setcomp, and if we restrict these things with an AppArmor profile, and if we run really tightened down like SELinux, we can do all these magical things, right? Now, to most people, that's just, it's not actionable, right? Here's a bunch of things we can do, but it's not consumable. And so, damn it, I was doing so good. Yes. All right. So this isn't really consumable, right? So think of like the iOS model, the Android model, where it says like, here's a bunch of things that you want to be able to do. This application requires things like network access. This application requires access to GPS. So what you're seeing now is a proposal to come up with basically a set of common entitlements, and be able to apply those kind of like in a cumulative fashion, right? So if your application or your container, for example, needs host network access, then we can basically, through a set of AppArmor or through a set of capabilities and syscalls, we can kind of come to a set of what you actually need. So here's an example. If we wanted to limit network access and we wanted to say this is a container with like network access of none, we could drop those capabilities and block things like netadmin, netbind, netbind service, netraw, and net broadcast. Some capabilities perspective, that limits the network stuff that we can do from that container. And then at the syscall level, so again, a lot of these are blocked by default, by, Docker's, default seccomp. But these would be things that we'd want to make sure that if we wanted to ultimately restrict that container and be able to talk network, we'd want to make sure that all those, syscalls, were being blocked, at the kernel level. And if we really wanted to get nasty, and confine that, further, then we could, for example, block access to a lot of different paths, things that containers, potentially things you can do to assume, additional privileges on that host. Things like, cap sysadmin. You see commonly, right, like if you want to lock down what that container can do, things like cap sysadmin have to go away. Ptrace for a lot of obvious reasons and what you can do to a running process. But ultimately, if you could take these things away, then you could ultimately neuter a lot of what that container can do. So this seems to be a more consumable way to present this. This isn't something that's like fully spec'd out. So there's a proposal, and then there's a couple reference implementations. But what generally the reference implementations are doing are spitting out things that you wouldn't be able to, like, for example, pump upstream into Kubernetes. And it doesn't necessarily make it easy to build these policies on the fly, because these policies may ultimately break a lot of what your container can need, or it could actually give you more than you actually do need, so you're over-privileging containers. But at the same time, maybe it's a good starting point to work from this. So again, how many of you Java developers understand SELinux? Maybe a couple of them, and congratulations, but not many of them probably do. So building policies is one of those things that we either take those defaults out of the gate, or you hire somebody that knows Linux, or you turn them off. So really you want to automate, probably what's the 80% there. So if you can use entitlement profiles to do these things, great. You can use the defaults that are there. But for example, there's also a lot of tools that you can use that have been around for a long time that'll let you build at least some form of an SELinux policy or an AppArmor profile that you can use. Now, they may be a little bit more liberally scoped than if you were going to build them by hand, but there's not enough people that can build AppArmor profiles by hand in the world, so we take some form of automation. So in regards to seccomp, if you're going to apply these things at Docker, you can just pass that as a command line configuration. If you're doing it via Kubernetes or another orchestration platform, then you would specify that via like annotations that you pass directly into a pod. So this applies to all three of these: seccomp, AppArmor, SELinux, similar methodology. But yeah, again, you can use the defaults out of the gate. With regards to AppArmor, the profile needs to be loaded in a similar way. So if you're doing it on Kubernetes, then each node actually has to be able to point at that AppArmor profile. Because looking at this here, if you're looking at what that wrapper looks like, it's just literally looking at a place you can pull in a JSON or other policy file. And the AppArmor default that's there, casts kind of the 80% net. But obviously there's a lot of things that you can do to squeak in between. SELinux is the one that everybody it looks like kind of a dark art to most people. And SELinux is, probably not the easiest thing to build by hand if you don't have a lot of familiarity with things and labeling. But there's different tools that we can use to build policies that we can use on the fly, right? So I would never tell anybody that I run into that's a Java developer to learn SELinux. But if they, for example, got thrown into doing this and they were the only person in their organization that could work on it, I'd tell them to automate and run policy, ultimately see what breaks, right? Apply it. Similar if anyone's ever built like a CSP policy for the web, right? You'll run CSP for a little bit, see what types of violations happen, rerun that iteratively, but you'll generally run in some kind of observe mode, and it's similar to running things like AppArmor or SELinux in permissive mode or a complaint or report only type of mode. That's generally how you learn, but then you'd actually want to enforce if you're running in a container in production. And things that you can use to, instrument your application and learn about these things like ptrace. Those are harder to run like production, in production, or I wouldn't necessarily want to. So some of these like, deeper kind of instrumentation and audit tools, I would want to run in my testing pipeline, not in production. So that's pretty much a high level of what you can do there to harden containers. So what you end up getting is kind of a multi-layered approach. The container runtimes are the first place you think about isolation. Do I want to run a hypervisor? Am I okay with things like control groups? That equates to, how tolerant am I of a container breakout taking down the worlds? we deploy things as microservices, and we try to loosely couple components. But that doesn't mean that we don't cross-pollinate things. We don't kind of cross the streams with our systems. So when we look at how we build these things, right, don't just look at the containers. Don't look at the apps in our code. You kind of have to look at the entire stack to figure out what's happening and how you can actually bust into a container. And again, the isolation model and how you run is very much on your organization. If you're running things like managed services like AWS's EKS or running on things like Azure with their AKS service, you have a lot of things abstracted out like control plane. So there's things that you just may not be able to compromise in the same way. So depending on, if you're running in bare metal versus cloud, which is a topic for another day, but you also have a little bit more flexibility and the ability to take some of these things away if you don't have the same tolerance. But you lose some of that, lower level control that you would have if you could ultimately build a cluster from scratch and actually control the control plane. And that's my story for today, folks. Does anybody have any questions? Happy to answer. Yes.
All right. With things such as there are extensions to Docker, at least within the research community, of trying to extend them to also be secured with things like HSMs or TPMs. While this is another method of many other attempts to actually provide a seamless security model, do you see these kind of taking off, or do you see kind of vendors themselves further abstracting as a means of also providing more security? So do you think? I guess my question is more of an opinion, or your opinion of it.
Yeah, so you see probably more of a push to use hardware-based isolation and things like that. So things like RDT, right? So if you look at like runc, there seems to be more support and kind of go in that direction. With regards to things like TPMs for things like secrets, is that where you're going? Yeah, I prefer, some cases, so his question was, how can we use things like TPMs to further, segregate things like secrets, and TPMs are a good place. What you've seen is things like Docker, they do have first-class secrets, management APIs, and so does things like Kubernetes, but what they end up doing is storing those secrets somewhere, in plain text. So you can do things like use, Vault, for example, and you can have a way to, not store those in the cluster. But then those have their own issues where you use things like default, or use service account credentials to unlock Vault. So we have like shared credentials, right? But at the end of the day, you still have a way to unlock that if you can pop that. So Vault ends up being as ultimately secure as you can unlock it. So what you do see, especially like in the managed kind of service solutions, is that they're integrating deeper with like their key management solutions and HSM type of things where, they'll store the secrets and then you use some type of IAM, that the platform understands. It passes into the container. So on things like, Azure, and EKS, in reality, under the hood, they've done some optimizations to use their own IAM model to integrate with those things. So, the short or long answer to that is yes. I do like having a better way to store secrets than what's currently supported, out of the gate. It's a better solution than using things like environment variables and hard coding stuff into your, repositories, but